Okay, so we come to the next part of the introduction of chromatography. We will learn on how the efficiency value, the N, and the alpha will affect your resolution. Okay, basically this is the same notes being taught to you in instrumental analysis last semester. Okay, so we have four scenario over here. Okay, you can say it's a poor resolution because there is no complete resolution here. Okay, it's supposed to be something like this, not like this, so we call it as poor resolution. So resolution over here maybe is less than 1.5. okay, in this case we have good resolution. RS is maybe 2 something or 3. Okay, and also we have a narrow and slimmer peak as compared to here. Okay, and then what happen if you have good resolution still, but broader peak? Okay, so in this case, the resolution that you get, it is good because of the column selectivity, yani alpha. Okay, alpha here, column selectivity is between 1.0 to 1.4 kan. So it is depending on that only, but on N itself is low. The N is low, the efficiency, because it's not slim. It's not slim like this. Okay, it's broad. Okay, band broadening must be happening there. And here you have a very poor resolution. Okay, RS. They are not separated despite having good peak shape. This is tall and quite slim, right? But despite that, it's still giving you poor resolution. Means that you have to alter something else as well. Okay, and the selectivity is really low. The K that we want, the K prime that we want is between 2 to 11. But here you see that the distance between the word volume and the first peak is just few seconds away, for example. So this will give you K prime of 2 plus. Okay, the one that we want is between 3 or something lah, but 2 is still acceptable. Okay, as for here, you can see that the K prime maybe is around 4. It's around 4. Okay, here is only 1 point something or even 2. So that is the effect of the effect of the efficiency and alpha on the resolution. So how to make sure you get a narrow peak and also a resolved peak? We want narrow and resolved. So you have to take into account the Van Dam equation, who is taking into consideration of flow rate kan, flow rate and also the diffusion and column length. Okay, just now HETP equation is L divided by N. If you want low H, you should have high N, kan? High N and low length. Okay, so solid support. Okay, solid support is the stationary phase. You want small particle rather than large. And the liquid phase, the mobile phase should be in easily diffused so that it can dissolve the analyte better. And of course, the flow rate related to this Van Dam here, column temperature, as well as sample size. So if you are separating amino acid, for example, amino acid kecil je, drugs pun kecil. Okay, so it's easily absorb and dissolve as compared to large analyte, such as apa? Such as the albumin. So what is the albumin? So albumin is the remember when you is quite abundance in protein-based food such as eggs. So this albumin is really big. That's why you can see inside those egg. So imagine if you separate very big albumin as compared to small drop, you will expect to see a very broad peak as compared to this one. Okay, and of course this is high end and this is low end. So we come to the few final parts of the introduction of chromatography. Advantage of chromatography is high resolution if you optimize the parameter, and good analysis for complex mixture because it can separate, and good for quantitative analysis, you can calculate, but without the standard solution that you bought from the chemical company, you cannot get proper identification unless you have MS. If you have MS with the library, you can identify. It is unsuitable for preparative separation. This is related to GC and HPLC. Okay, so this is unsuitable for preparative separation because in preparative chromatography, you want to collect the final product. But if you are doing GC and HPLC, everything goes to the detector and then it goes to the waste. So you cannot really collect them, okay, as compared to the column chromatography, just like the natural product chemistry. So after this, we will go into the individual chromatography technique. First, we will learn about gas chromatography, and then we will go to the HPLC. So these two topics, basically you already covered it last semester. Most of you aced it, I think. Okay, so I'm going to go quite fast, and we can focus on the application as well as the tutorial. Okay, I think it's better like that. So in this comparison of chromatographic technique, you have to understand the difference between gas and liquid. So gas and liquid column, we call it as gas liquid chromatography. So this is W coat. Okay, wall coated open tubular. Okay, if it's GSC, is the P coat. P coat or the pack column. Okay, so because there is a solid inside it, the adsorbent. Okay, as compared to liquid, HPLC, mobile phase is liquid, of course. The stationary phase is C18, so it's solid. So you can have a lot of different packing, adsorbent, bonded, resin, or gel. So if you have adsorbent, you go towards the column. Okay, and then you also have based on gel, whereby you have size exclusion column, size exclusion chromatography over here. So if your stationary phase is liquid, it is not liquid per se, but it is more like adsorbent being coated with liquid outside it. So you can have this one, LLC. LLC stands for liquid chromatography. Okay, and then we will also have TLC in the terms of liquid and liquid solid. So this is the summary of between classical column chromatography, TLC or paper chromatography, HPLC, and GC or SFC. So basically these are our conclude everything that you learned last semester. Okay, you can have a look lah.